So last time we saw 2 or 3 concepts. First was tree, then there was balance tree, and third was search tree. Right, and we'll always assume binary. So binary tree, then balanced binary tree, then binary search tree. So for when you see the keyword balanced, then you can invoke this theorem, which says that for size n balanced binary tree, the height is always at most log n. So although the space is n, still somehow the access will be very fast because it is the height is only log n. And the third concept was this notion of search. So the height will be useful only when you can actually use the height properly. So for that you have to arrange that orange tree. It shows that every node V, the left, all the elements have to be less than equal to V value, and then that should be less than what you have on the right, whatever you have on the right. So these were the examples. In green tree, how do you search for 29 and how do you add 50? Any questions? How do you insert 50? And so search, in fact, we even wrote the pseudocode, how to search for X in a BST T. And similar thing for insert. Okay, so if you want to insert X, then you should try to search X. You will not find it, and wherever you stop, there you insert X. So both these operations are order height. In fact, they are exactly, you will take as many steps as is the depth of this node X. Is that clear? So, yeah, as an exercise, you can write down the pseudocode for insert. So, this will be very similar to search, just you have to create a new node. More interesting exercise is convert a BST into a sorted array. In linear time. How do you do this? What will be the pseudocode to convert a BST into a sorted array? This is the reverse problem. Directory we could have seen as an array, but so the opposite question is that suppose I give you the directory, can you convert it into a, well, if I give you a BST, can you convert it into a directory, into a sorted array? How do you do this?
We can use a stack.
No, we don't know stacks.
We can use the recursive call. Recursive call for root and left.
Yes, so this binary search tree is inherently a recursive structure. So you can, for example, in this green one, you just have to keep on going. Basically, you try to find the min. So in the tree, the min is 5, right? So you will go left, but it may happen that this at some node left does not exist, so you'll be forced to move to right. That can also happen. But then you basically try to stay on the left side as much as possible. So that will help you reach the minimum, right? And then from the minimum you can find the successor. and the successor of that, and so on. So you can write down the whole array. It's an interesting pseudocode. So you should try this as an exercise. It's a simple recursive call. And third is the opposite, which is convert a sorted array. In fact, I should not say this is harder. This I think we have kind of done pictorially already. So convert a sorted array A into a balanced BST. Even this you have seen in order and time. So how do you get both search property and balanced from an array? The array is given to be sorted. So this is how we invented tree in the first place. Sorted array, you look at the mid, call that the root. Right, so that is the root pointer. You can create in parallel a tree structure. So the mid will be the root, and then what will be the children? Yeah, then you have to look at let's say mid by 2 and mid times 3 by 4. So those will be the children. Right, so by a simple arithmetic, you can actually make in parallel as you are accessing the array a tree, and that will be a balanced binary. So two things are here. Why will it be balanced? Well, because of the arithmetic, you are using mid and then you are using mid by 4 and mid times 3 quarters. So because of that, it will be balanced. Why will it be a search tree? That is because of sorted assumption. Right? So it will be a balanced binary search tree. Binary because you are looking at only 2 children. So this is just a sophisticated binary search process. And number 2 is the opposite. It's actually similar. In fact, number 2 is slightly harder. So you have to think about this recursive function and give the pseudocode. Okay, so try these things. These are very short pseudocodes. Yeah, so just can give a hint for 2. So in 2 you are given BST, right? So what you have to do is you should just recursively print v dot left, v and v dot right. So if you just do this, let's say you start at the root, you print, you basically print or traverse the left subtree, the root and the right subtree. So this is the thing which you are printing or you are traversing. So v is already a value, so you can just put it in an array, or you can just print it, and the left part will be done first, v dot left. But that may not be a node. It may be a subtree. So, but you can call print on the same in the same way, and then that will again blow up into its left child, parent, right child, and so on. So recursively, this will print your sorted array. No, I will not repeat. This is just a hint. So build on this, give the pseudocode. Because if I repeat, I have to actually give the whole pseudocode. That will take unnecessary time. So you do this as an exercise. This is how the recursion will proceed. It has 2 calls, 1 print. Okay, so v dot left is recursion and v dot right is recursion. So 2 recursive calls. And the middle thing, the parent is being printed because that is a single node. So think about this. Okay, other question is, so with this type of insert and search, can we say that depth of T or height of T is equal to log n? Is this true? So the pseudocode that you have seen for search and similar thing for insert, slowly you can insert and build the tree, the binary search tree. But what will be the height? Is there a guarantee that the height will be log of the size? No. Just use these two operations, insert and search. There is no other promise. Then what can you say? Then it may not be balanced. Right, because the problem is that the way these values or integers are coming, that may be arbitrary. So what may happen is you may first get 46 and then you may get 28. So 28 you will insert here, then you will get 35 and then you will get 29 and so on. So what is happening is that this is not balanced at all. Right? If you get numbers in this sequence, so you will be inserting, first you insert 46, then you insert 28, then you insert 35, then you insert 29. So this is actually giving you just a single link. This is not binary at all. This is just simply an array which is in bad order. So if this is the kind of insertion or sequence of insertions, then the height is what? It's n, right? So height can be order of n. So insertion sequence can give height order of n. So this is a big problem. In fact, the original problem is not yet solved. So this insertion could be in the worst case. So this is the worst case. I mean, in the good case, this will not happen. But in the worst case, you can see this example, it is happening. So in the worst case, since we always care about the worst case, so in the worst case, this can be as big as the number of, not even order n, it can just be n. So the height can be as bad as your array size. So this has not solved anything. We are only imagining good cases. We have not handled the worst case. So for that, the solution is to change the pseudocode of insertion. That has to be made more complicated so that it is balanced at all times. Okay, so this we'll do probably next week. So the correction is insertion algo needs to make sure that T is balanced binary search tree. Okay, so it should have all the properties: binary tree, balanced, and search. So which would mean that the height will be log n. Okay, so height of the tree will be logarithmically related to the size of the tree. So yeah, I will not, probably I'll give the pseudocode next week because we'll do a more sophisticated tree. Generally in the syllabus you see red black tree. So we'll try to do that. So we'll design something which is called red black tree. It will be a sophisticated BBST. And the idea of insertion there is rotation. So rotate to balance. Have you seen this before? Red black trees, or how to rotate when tree becomes unbalanced. So that is the main trick. Very simple example is what you, so when you have 49, 66 and 50, right? So is this tree balanced or unbalanced? This is unbalanced because 49 has 0,2 left versus right. So this is unbalanced. So the way to balance it is you rotate in the anti-clockwise direction. So let's say left rotate or anti-clockwise rotation. The unbalanced subtree. So when you do this rotation, then what will happen is 66 will become the root, 49 left child and 50 right child. Then it will become balanced. Okay, so pictorially this is what you want to do. So if you inserted 50, it made your tree unbalanced. So the direction in which it is unbalanced, opposite rotation you do, and then you will get a balance, single rotation. Okay. So pictorially it is simple to see, but when it is written as a pseudocode, it is massive. Okay, there are all these new number of cases, border cases, and things you have to do. So let me postpone that. We'll do it more systematically when we get time. Since somebody talked about stack, let us do stack first. Okay, because stacks are much easier. They are almost trivial. So let's do that data structure first. So this is stack. So what is a stack? Any guess? The name is not very suggestive. Stack is what? Is it an array? With what property? So what is the mathematical modeling of this DS? Right, so it is like an array which is growing from 0, 1, 2, ... n minus 1, but then you are not allowed to access any cell in the array except the last one. Okay, so it is you can think of it as an array where only the last place is open. That's called the top. So the top is accessible. The element there is accessible, but nothing behind the top is accessible. Everything else is inaccessible. Right? So which seems a stupid idea, because when you can access every element, why would you tie your hands? Okay, so the only way to make sense of this is take a problem which needs this. So the problem is expression evaluation. Sorry? No, I'll give the mathematical modeling. The modeling is that it is a data structure where there is a base which is sealed and then there is a top which is open. So you can push in the top, you can push an element in the top and you can pop an element from the top. And there is no other operation. No, there is no, you cannot, generally you don't know the address of anything except in an array. So yeah, the modeling we will do, so to make it formal, but let's take the problem first. So the problem you want to solve is expression evaluation, which means you are given, let's say, an arithmetic expression. So expression is 3 plus 4, then there may be parenthesis. Right, so this is something which computers do from day one. Right, you give them expressions and then they will evaluate them. And you also do it early in school. Right, so what is the rule for this? There is an acronym, BODMAS. Right, so you apply BODMAS and then you calculate this value. So you have to start from what? Do you start from 3, 4 or something else? So starting from 3, 4, 5 will not help you at all because you have to start from the innermost, which is 8 plus 9, right? You have to solve that, then multiply with 6. But remember that 5 could also be, so 5 minus 6 you can do first, or you can do 6 multiplied by 17, right? You had two options. So there has to be a policy which one comes first, otherwise there will be huge ambiguity. So, and computers hate ambiguity. So you want to give them very precise rule. So the rule here is that first multiplication will happen, then subtraction will happen, and then the bracket value is calculated. Right, so believe it or not, this is exactly what stack is for. Okay, stack works beautifully in this. So the advantage of stack is that so if you were asked to write this program that is given an expression, you calculate the value. If you were not organized, this will be quite expensive because you have to, I mean, you can look on the slide here, but the computer cannot look at the expression as a whole. It will only look at few numbers there, right? So it will not know where to start from, whether to start from plus multiplication minus 3, 4, 5, 6 or what. Everything is equal for the computer. So you have to, in the pseudocode, you have to somehow then search what place to go to calculate first. And then what is the next operation to be calculated and what is the third operation and so on. So it will be very hard to implement this in a linear single scan. Right, so the goal is to implement this or calculate this in a single scan. So you just do a read in sequence and evaluate the intermediate answer, then the next answer, then the next answer, and the final answer. So expression evaluation in a single scan. How do you do this? Right, this looks quite difficult. In terms of pseudocode. So this is what we will solve. That's why stacks are helpful. So you have to write a program whose input is an expression. But then we have to say how it is presented. So how is the expression presented to the machine? As a string will be, you have to do string matching, etc. Let's say that it is presented in an array. So which means that 3 is the first element, plus is the second element, 4 is the third element, and so on. Okay, so you can present this neatly in an array. I mean, string is also an array, so that's not very far. So string or array is given to you. It's actually equivalent. And in the output you have to give the value. Okay, this is the problem you want to solve. Well, by hook or by crook you can solve it in brute force. Although even that will not be trivial. It's a good programming exercise. But we want to solve it as fast as possible, like almost one scan or two scans. Okay. So an order n algorithm for this inspires stack. Yeah, so at this point it may not be completely clear why this is anything to do with stack, because the input is just an array. So why in an array you can access anything you want, but yeah, somehow it will gel well with stack. So you are actually restricting the operations that you are allowed, and that is forcing you to give a faster algorithm. So let's state the mathematical model that we are calling stack. So stack is basically a list where all the operations happen at the top only. So what does that mean? It means that you have list is of these elements, and maybe we will. So how do I want this? I think I want the other way. Okay, it doesn't matter. So for now, let's just say that this is the top, and this is the base. Yeah, somehow I don't like this. Let's change this. Let's call this the base and this the top. So in the list you are not allowed, you cannot access anything, as the model says that it's a list where every operation will happen at the top only. So you can only, either you can insert at the top, which means that en will be followed by another element, let's say en plus 1. Or if you want to delete something, then when you say delete, en will be gone. So top will become en minus 1. Okay, so the base is not a pointer. Base is just for name, but top is where the pointer is. Okay, this is a pointer that you have available. And you don't have any other address available, so whatever you will do with respect to the pointer. But when you, the good thing will be that when you do the pop or delete, the pointer will shift to get the address of the previous one, which is an minus 1. Okay, so to get the access of internal elements, you have to remove the the top elements. Then you get to that address. So that will be the cardinal property of stacks. So to access the ith element from top, it takes how much time? So in an array it would have taken order 1 time, and here it will take order I time. Okay, that is the only difference between array and stack. That here if you wanted ith element from the top, then if I is n by 2, you are taking almost order n time. Because you have to delete 1 by 1, then you will reach the middle. And you have to go through everything before. So you will get an, then an minus 1, and then an minus I plus 1. Okay, so you will have to go through all these elements. So it's basically, you can think of the top as a mechanical arm. So when you want ith element, then the arm cannot just jump directly. It will go 1 by 1. Okay, so it's like a mechanical arm which has to move all the way to the ith element. And what are the query operations in the model? So query is get something from the list, so is empty. That's one query you can do, whether the stack is empty, stack S is empty. And more important is, what is the top of S? This returns the top element, which we are calling here an. Okay, so this is just query. This will not edit anything in the stack. It has only read permission. Now for the write permission, you need these update operations modeled. So this is create empty stack. As the name suggests. Second is more important, push. So what will push do is, it will push the element x in the existing stack at the top. And then change the top. The top pointer. Right, so push will basically create a new node x, put it at the top, and makes that the new top. So size n stack becomes size n plus 1. And the destructive version of this is pop, which will just do the opposite. So it will delete and output the top element. So when it outputs the top element, it deletes it and then changes the pointer. Is that clear? Right, so this is the mathematical modeling of a stack. So you have the stack S stored somewhere on the hard disk, and you can talk to it only through these operations. There is no other operation available. So you can either create an empty stack or read what is written on top of the stack, or you can pop the top, you can push, increase the size of the stack, and so on. So these are the only 5 operations which are important. So if when you push, for example, if you push X on the stack, A1, A2, let's denote the top as this. Then what it will become is A1, A2X. Okay, so X will go at the top. So now the stack is of size 3. And when you pop from this stack, what happens? It becomes, so it gives you, it outputs A2, and the stack is this. Or maybe for more effect, let's make it bigger. So it will output A3 and it will give you A1, A2. So A3 is the return value, and the stack changes. The side effect on the stack is that. Okay. So any questions? So now let us see a sketch of the pseudocode for expression evaluation. Okay, how will this one access data structure help in evaluating expressions fast? So we want to see that we want to see how this stack formalism will help in expression evaluation. Before that, I have to remark that how will you implement stack? So stack can be implemented as an array, first of all. I mean, you can say that S is an array where the top global variable top can be stored separately. So there is an array S, and there is a length of the array, for example, is a global variable. So if the length is you have to change some n-1 probably, but whatever. So the last cell of the array you can store what is the index of that. So when you want to do top S, you should just check what is the last cell value in the array. When you want to push x, then what you have to do is you have to go to the index last plus 1, update the last cell index, go there and put x there. So this, ultimately it will be a problem to keep growing the array, because I think the best way will be you use a linked list. Okay, so in the linked list you can, so if you want to implement this stack in a fast way using linked list, where should the top be? At the last? Yeah, you should have wherever your pointer is. So if you have the head pointer, then that should be the top, because immediately you can go there, you can read the value or you can delete it and update the head to the next node in the linked list. Or if you want to push, then you can just create a new node, make that the head, let it point to the old head. Right? So linked list would be a better implementation and a fast implementation for stack. So this you have already seen, doubly linked list implementation, just use that. Because in an array it is not easy to change the length of the array. But in linked list you don't have to worry, you can have as many nodes as your hard disk supports. So use that to implement stack in practice. Okay, everything can be done in how much time? The operations will take how much time? Sorry? Cannot hear. O of n. Why do you say n? So there is only top, you just access the top. Everything is O of 1.
Why do we use the doubly linked list instead of?
Not very clear. I think depends on your implementation. So what will you do with this update operation pop? Yeah. Yeah, I think you can do that. Yeah, you can just remember the node next to the head and delete the head. No. The top is the head of the linked list. Yes. Yes. No. One pop is you just have to remove one node. That's all.
How will you remember the previous pointer?
The previous pointer. No, so there must be some misunderstanding. Because if this is your head of the linked list, which now we are also calling top of the stack. So when you want to pop, the head goes away and it is updated to this one. Because you can always store this. Before killing the head, you store what it points to. Yeah, so that is that. All these things are very easy. So with that, so operations will take only order 1 time. Okay, so just remember what the doubly linked list was and what stack is, and you can see easily that all these operations are very cheap. So that is one of the advantages, that these operations will just be constant time, easy to implement. Okay, so we have just enough time to dry run this pseudocode for expression evaluation. Okay, so let's do that using stack. So let's see the idea for expression evaluation. Through an example. So let's take this example of, it's not too long. So 8 plus 3 times 5 raised to 2 minus 9. Okay, so this is given to you in an array. So let's set some notation. So this is called an operator. So operators here are, how many operators are there? 4 operators are there here, right? And so plus multiplication and minus, these are binary operators. They expect 2 inputs, and obviously they will give 1 output. While this exponentiation expects only, well, I should not say that. It's also binary. It expects both 5 and 2. Okay, so yeah, so these are all binary operators. But as you know, plus and minus can also be unary operators because they may just be sign. Right? You may have just minus 9. So plus and minus may expect one input, but usually they will expect 2 inputs. And exponentiation always needs 2 inputs. So these inputs are called operands. Okay, so you have operands in the array and you have operators. This is given properly in the input. Right, and now the program that you have to write should calculate the value of x. Is the setting clear? Is it clear what are the precedences? What is the precedence rule here? What we should be evaluated first and then next and so on. Because this order here can be important, right? Should 3 times 5 be done first, or 5 square be done first? Yeah, so there is a third thing which is called precedence, which you should have learnt in school, which is that the wedge or this exponentiation has more precedence than multiplication. What is the precedence between multiplication and division? Division comes first. Okay, let's believe you. And then this has precedence over addition and subtraction. So what is the comparison between them? They are equal, right? So these are the, this is the precedence rule for the operators. Yeah, there is one more, there is a sequence of more important operators which we will come to after we have solved this problem, which is parenthesis, right? Or parenthesization. So you can parenthesize in many ways. There are 3-4 kinds of parentheses, and they have their own precedences. And all of them, how will they compare with these operators? They precede. They come first, right? If there is a parenthesis, then you first focus on the parenthesized part and don't worry about what is outside. So parentheses get precedence over this, but we'll get to that later. It will be very similar. So let's not mix up with parentheses. Right. So how do you do this in a stack style?
start adding elements along with the operator, when we reach the exponentiation, we will do the exponentiation.
But why?
Because it precedes all of the other operators.
No. Yeah, so that's the part where you have to be careful. So it is not you who is doing this, the computer has to implement this, do this. So in the pseudocode, what is the check that tells the computer that exponentiation has to be done immediately?
You can just add a statement that if the operator is exponentiation, then we'll do it. Otherwise, we will just add it to the stack. And then in the second scan of the stack, we will do the next operator.
Yeah, so yeah, it sounds nice, but it will be tough to give this in pseudocode. So we have to see these steps actually, and stack will provide a very clean algorithm. So the point is, I mean, what the student is saying will ultimately be done. But what you have to be careful about is that since we are, I mean, if we are willing to use stack, then in stack you don't want to compare the top with something in the middle. That will be costly, and in fact you can think of it as inaccessible. So you can compare the top only with things 1 or 2 level below the top, not very far away. Right, so when you reach the wedge, so you will be actually storing this in a stack style. So the array is like this, and this is your top. This is the input. So first we will push it in this order in a developing stack. We'll do this tomorrow. And we'll see 8, then plus, then 3, then star, then 5, then wedge, then 2 and minus. So now when you see wedge, there has to be a rule which says that wedge has to be calculated immediately. Unlike plus. Right, so you did not decide that 8 plus 3 has to be calculated immediately. So the pseudocode at that point should not say immediate calculation, it should wait, and it should attack only when it sees wedge. So we have to set up a logic tomorrow of why or how wedge is different from the previous operators that we saw.
So why is minus and 9 is considered in the same role?
Sorry, minus is what?
And 9 is considered in the same role.
Oh, no, this is a mistake. Okay.